Okay. Morning, everybody. Uh, Welcome back. Um, let's see. How are folks doing? So we started today with a stream at 8 as well, although we didn't have, there weren't very many students at 8, which isn't surprising, but looks like we don't have very many right now either for some reason. So let's see. Um, I posted the quiz and the quiz corrections to Blackboard. It does not seem to be updating for some reason. I don't know what the deal is with that. I'm working on it, so well, I think it's some kind of bug with the homework system, but that stuff should all appear there, so you can kind of see where you're at. I'm working on that now. Uh, we should have another quiz this coming week. I'll probably make it available to you over the weekend, but on Newton's laws, this is a central subject of the course, so it's something you really need to know and demonstrate that you know. But um, not inclined to do like a big exam because I feel like the online options are not great at this point. So we'll do another quiz, sort of something of a similar scale. We'll try something on Blackboard is my thinking too, and see how that goes and improve from there. Um, Basically, I just don't want technical issues and problems and stuff like that to be messing with your head and your ability to just show that you can do physics problems. So we'll try and do that in kind of the most logical and painless way. There's enough online systems and stuff that we're dealing with that we'll try and make that less of an issue. Um, okay, so, all right. We're going to talk about circular motion today. We started talking about that last time, but I really only threw it to you at the end. So no, yeah, you have spring break in that we don't have any activities tomorrow. So if you had lab tomorrow, there's no lab tomorrow. Yeah, that's a good question. So yeah, it's not much of a spring break. It's just Friday, long weekend, and it's not like we can really go anywhere because everything's locked down and everything. But um, maybe take some time to yourself where you're not staring at a screen. I think that's what I'm gonna try and do myself. Read like a paper book, something that's not glowing. I feel like that might be a nice contrast. Um, but yeah, a little chat before class just about kind of, you get kind of wiggy, I think, staring at phones and screens and tablets and stuff all the time. So maybe it'll be good tomorrow to take or end the weekend to take some time not doing that. But before we can do that, to the matter at hand, circular motion. So we introduced this topic last time, but we didn't talk about it very much. Uh, Let me take a second and kind of uh, discuss that. So this is analogous to a lot of what we did in chapter 2 in that we're looking, we're going to kind of connect to describing motion, except now we're describing motion of something that's rotating. And it seems like a little bit of a jump because, section 5.1 was on friction. And now we're going to look at 5.2 through basically 5.4, which is on circular motion related topics. But where we're headed is to chapter 6 is on gravity. And we can kind of connect this to this, and then we'll connect this to this. We need to understand some of these topics before we're able to mess with gravity. And so the picture that I want you to have in your mind is we have something that's rotating in a, if I can draw a circle here. We have something that's rotating in a circle. It could be, for example, a mass on a string. So that object it has some velocity. The velocity is actually tangential to the circle. And there is an acceleration that's associated with this, the centripetal acceleration that's directed in. And we have a scalar relationship that the size of that centripetal acceleration is equal to the velocity squared over r, where the radius of our circle is r. Okay. So a couple things. The velocity and acceleration are perpendicular, which is kind of interesting. This is different than what we've done in the past. Normally we think of acceleration as in the direction of velocity, right? If you speed up, those things are, the acceleration and the velocity are in the same direction. Well, this is a little bit different. This is a scalar relationship. In other words, the relationship doesn't contain the direction information. But it allows us to quote the size of the acceleration. It gives us the magnitude, the size of AR. So when you're thinking about this, don't think of it as v squared over r causes the acceleration. It doesn't. Think of it as descriptive. It's telling you the size based on the conditions. You need something else to provide the acceleration. And yeah, you need something else. And there's different sources for this. It could be tension. You could have a string, an object on a string, and it's actually the force of tension. And I'll show you an example of that. It could be friction. Imagine like a surface that's rough, like a turntable or something. Think of a spinning a record, and if that surface is got grooves on it or whatever, a record would have grooves and stuff on it. And then if you plopped something on top of the surface, there would be a force of friction that would provide the centripetal acceleration. Or where we're headed in chapter 6, it could be that you have, like a celestial body like the sun, and there's a planet, and it's actually the force of gravity that's providing that centripetal acceleration. So, and that's where we're headed with this. So in other words, you need something to provide the acceleration. This relationship tells you the size of the acceleration. Okay, so the next ingredient, so that's basically section 5.1. It's telling you this relationship between the centripetal or radial acceleration. We'll use these terms in interchangeably. Radial. Come on, pen. What's going on here? Shoot. Ah. Sorry. My pen is not cooperating. Kidding me, pen? All right. Ugh. So radial or centripetal? I'll try and use AR, but we'll talk, we're talking in about the same thing. Okay, so, all right, so how we connect this to what we've been doing in chapter 5 is that basically by direct analogy, we've worked in, if you look at the sum of forces in x or in y, you can find the acceleration in x or y, etc. Now we're talking about a situation where if we look at the sum of the forces in r, that's going to equal, thinking about Newton's second law, the mass times the acceleration in r. So in other words, the sum of the forces in r is going to equal mv squared over r. So, and this is basically, you know, Newton's second law, the radial addition here. Okay. So, I think I tried to show you this before. It's not super visible, but just to have an image of this in your head. Here I have a fishing weight on a piece of string. If I spin that, in this situation, it is the tension in the string that is providing the centripetal acceleration, okay? And we can do things like, so granted, this is more complicated. I'm driving it. You can see my hand move. There has to be some where I'm putting energy in. But if I speed it up, suppose I go twice as fast, the tension actually increases by a factor of 4 because the sum of the forces is proportional to v squared, or in other words, the centripetal acceleration goes like v squared. If I could keep the same velocity, so it's impossible for me to demonstrate this, but increase the radius, you see it's getting floppy, the tension is decreasing as r increases. What else? So I'm trying to demonstrate to you like a horizontal situation where it's flat, but you could also imagine, and we'll look at this in a second as well, the situation where it's vertical, where you have the thing spinning in a circle vertically. And this situation is a little more complicated because I'm not keeping, the speed is not constant. It's accelerating as it falls, right? Similar to looking at free fall. It's going faster at the bottom than at the top. So let me switch back to our whiteboard here. I think kind of a key idea with this, and I should have emphasized this more at the top, so I'll put it in a different color. I'll use a different color. Come on. I have different colors. Let's use a fun one. OneNote, come on. So kind of a key thing here is that you can have acceleration just because you're changing direction. Put in here, how about? Only due to change in direction. So in other words, the velocity, the magnitude of the velocity, i.e. the speed, can be constant, but you're still accelerating because you're going in a circle. You're changing direction. So okay. So, and an example that can help you see that is if we imagine this situation with the string, right? So suppose our string breaks, okay? The object is not going to go like that. The object is going to continue to go in the velocity in the direction that it was going. So, oh man, my picture is not very good. If our velocity is like this, When it breaks, it doesn't go off like that. It goes like this. It continues in this direction. And there's a little drawing of this, I think, in your textbook. And this is an expression of Newton's first law. An object's going to continue to do what it's doing. It's going to continue. If it's stationary, it will remain stationary. Or it will be, if it's moving in a straight line, it'll continue moving in a straight line unless acted upon by a force. Well, in this situation, it's the tension that's providing that force. It isn't changing the speed, but it is changing its direction. And as a result, it's accelerating. Okay. Okay. So that's sort of could have been a little more organized about that, but that's I think that to me is one of the key ideas about this is that you can have an acceleration due solely to a change in direction. Okay. So let's look at this a little more detail. This Newton's second law, basically for a radial situation. So the situation that I showed you, where I was, think of this as like the overhead case, where it's difficult to draw this in such a way that you can tell that it's like a circle. But imagine instead of a circle that we're looking at in straight on, we're kind of looking at the, let's call this overhead slash horizontal case. So in that situation, the velocity, is tangent to the circle. This would be the centripetal acceleration would be pointed in, and then maybe just kind of tough to be consistent with the colors and stuff, but just so it pops and just to distinguish, we would also have, oh man. Try my best to draw this here. Okay, so we would also have the tension force that's pointed in. So part of the reason that the drawing in this case is kind of crappy is that both the acceleration, AR, and the tension are pointed in the same direction. So, and you shoot, how long, can you hear me now? Has it been dead for a while? Ah! Okay, sorry about that. Technical difficulties here. Oh, okay, okay, cool. I was concerned I've been just talking, blathering on, um, without any sound. Okay, I appreciate the chat. Yeah, when stuff like that happens, flag me and I'll fix it. Because I don't want us to, I don't want to waste your time. Or I don't want you to be, be unable to hear. So I really appreciate the feedback. Sweet. Okay, so where was I? So this was the horizontal case, the overhead case. Let's compare that to basically, the vertical case. So this was me, swinging it in front of you. I cannot draw a circle. So in this case, it's a little more complicated. Um, so I'll put here sort of a caveat, and that is that, velocity, the speed is not constant. Because it's speeding up as it goes to the bottom of the circle. Yeah, exactly. So since it's inversely proportional to r, if by the same token, if r was to get small, then the tension would get large. Yeah, good point. For the same velocity. Um, so switching from sort of the horizontal, the overhead case to the vertical case, this is, and we'll come back to this. It's not constant since the speed at the top and the speed is at the bottom are not going to be the same, but we can compare the top and the bottom. So let's look at two cases. So, but bear in mind, it's a little bit confusing, or it's a little bit of a lie when we're talking about this, because this is with the assumption that it's v squared over r. But if v squared is changing, then it depends on where you are in the circle. In this case, in other words, so at the top, what do we have? So this is still with the string. Imagine, you know, this is a mass on a string. So in this case, we would have the tension in the string, but also, oh man, this drawing is going to be terrible. We also have the weight. And then I'll make this red again. We also have AR, the radial acceleration. They're all pointed down. Oh, so this stuff that I drew on the right, this is just supposed to be, sorry, just looking at the chat. If the velocity goes up by a factor of 2, then the tension would go up by a factor of 4. It's proportional to v squared, etc. Yeah, yeah. Anyway, looking at the vertical case, so it's kind of, insofar as the drawing is kind of crappy, but you can see everything is in the same direction. So if we then, let me make it black again. Come on. If we look at the sum of the forces in the radial direction, what are we going to have? We'll have, so something that came up when we talked about this before, this radial direction, that's the direction of AR, okay? So right now it looks like it would be negative if we were talking about x and y, but it's positive because it's in the direction of AR. So the sum of the forces in the radial direction, what do we have? We have a positive tension force. We have a mg. That's going to all equal MAR, where we'll replace the AR with v squared over r. Okay. Okay. So we can ask questions like, well, and we'll look at this as an example question. What is the minimum actually not velocity, let's call it speed. So like, what would be the minimum speed that will get you over the top? So what would happen in that case is when you get to the top, the tension would go to 0. So you would have just enough speed for the tension for the weight to provide the centripetal acceleration. So in this case, what would happen is this would be sufficient. mg would be sufficient. This would go to 0. And so we would then notice, oops, mv squared over r. Notice m is on both sides of here, so it doesn't matter. It doesn't depend on m. And then we could solve this for v, and you get this really concise expression that the v would be gr. Okay, so that's telling you, the speed that you would need. And you can apply this kind of logic to problems like, suppose you have a bucket of water, and you swing it over your head, or you're swinging it vertically. How fast do you have to swing it so that the water doesn't fall out of the bucket? In that case, it's a little bit different. It's not that, I mean, there's tension in the string of the bucket, but there's also a normal force on the bottom of the bucket that's pushing on the water. And if you're not swinging it fast enough, the tension and that normal force are not sufficient to keep the water from falling. But it's the same, it's the same kind of logic. Okay. So the other situation that we can look at, so this was basically the top. We can also look at the bottom. Now in this situation, mg is pointing down. It's always pointing down. But the tension force is pointing up, and I'll continue to try and keep AR in red just for contrast. The centripetal acceleration would be up. It's directed towards the center of the circle. So in this situation, oh, wait a second. Let me make this black. Oy, oy, oy. Looking at the radial components, what do we have? We have the tension, which is positive. It's in the same direction as AR, but now the weight is pointed down. It's pointed out. And in this case, this would, well, in these problems, this then equals mv squared over r. Let's see, questions. Yeah, so in terms of giving your eyes a break, yeah, looking out the window for a while can help. I've heard something anecdotally about how younger people were more susceptible to being myopic, that is nearsighted, because we spend so much time looking at screens that are right in front of us. It's good to get outside and look at trees and look at stuff that's far away. With regards to the question, please explain why the tension is 0. So that's the case. This is for the case when you're at the top. The tension is going to go to 0 when mg is sufficient. So let me put it this way. For speed low enough that mg is sufficient to provide the centripetal acceleration. In that case, the tension goes to 0. Okay. And then back to the bottom case, the case at the bottom. So like I mentioned up here, it's not the case that the velocity is going to be the same. But for sake of comparison, let's find the tension. for velocity up here. Okay. So that is V equals GR. So if we do that, we can solve this expression for tension. mv squared over r plus mg. Notice now if our v is root gr, we can just put that in. M root gr squared over r plus mg. You can see this will be gr over r times m. So in other words, it's another factor of mg. So this will equal 2mg. So for that, if you were to use the minimum, if the velocity at the bottom was to be the minimum, like what's required at the top, the tension in the cord would be 2mg, 2 times the weight. And granted, this is a little bit, like I said, this is sort of contrived because it wouldn't generally, it's not going to keep the same velocity, but you see what I'm saying. It's nice in that it gives us a convenient kind of number to compare. So that's a couple cases of this. Let me show you an example of this kind of idea, except with numbers. Let me see here. So here's our bucket problem. Oh, come on, man. Okay. So a bucket of mass 2 kilograms is whirled in a vertical circle of radius 1.1 meters. At the lowest point of its motion, the tension in the rope is given and it's 25 newtons. Find the speed of the bucket, and then how fast must the bucket move at the top of the circle so that the rope does not go slack. So this is the same question as the example I was talking about. Let's give ourselves a picture. So we've got a bucket. It's being whirled in a vertical circle, the radius of which is 1.1 meter. At the bottom, the force of tension 25 newtons. We want to find the speed of the bucket. So let's put in the rest of our forces. We're going to have the weight of the bucket at the bottom. We have the force of tension, and then I'll try and set off the acceleration again in red. The centripetal acceleration will be directed inward. Maybe I'll just draw this. Okay. So for part A here, we're given the tension and we want to find the speed. So kind of very similar to what we did above, but let's look at the sum of the forces in the radial direction at the bottom. What do we have? We're going to have the tension force is in the same direction as AR minus mg. That's going to equal m AR, but we know the magnitude of AR is given by v squared over r. We can find mg. We're given the tension. We just need to solve this for v. So how would we do that? We would multiply this by a factor of r, divide by a factor of m, take a square root of the whole situation. Okay. Can we restart? So this would give us the velocity of the speed, rather, of the bucket at the bottom. So we can put in our, let me find my notes here. We can put in our numbers. The radius was 1.1 meters. The mass was 2 kilograms. The tension was 25 newtons minus 2, minus the weight. So that'll be 2 times 9.8. Take square root. And this would give us a velocity of 1.7 meters per second. Okay. So the picture, yeah, so just to clarify, we're just considering the situation at the bottom. So the bucket at the bottom, it's swinging around. Oh, I neglected to put in one component here, right? So this is, it's got some velocity. So how about we call this one at the bottom VB and the one at the top V top. So for this situation, when we're looking at the bottom, we're solving for V bottom. We find that it's 1.7 meters per second. Ah, cool. Yeah, so it looks like this is a question that they've looked at in tutoring as well, or similar. This question of kind of the bucket is pretty classic for this for talking about this idea. You will find, and this is directly relevant to your homework assignment. I think there's a question that looks at basically the same idea. And the RCAS tutoring channel it's one of the featured, it should be one of the featured channels in our channel. So if you're looking for additional stuff, variations and similar stuff of this vein, if you look on there, it should be linked so you can find it through YouTube. So I don't know, does that help with the explanation of the picture? So let me let's also look at the top. So at the top, that's going to again be the case where now mg, the weight, and the force of the tension are pointed down. In the same direction as the centripetal acceleration. And in that case, when we go to sum the forces in R, we're going to have the tension is positive because it's in the same direction as AR. The weight is positive. It's also in the same direction as AR. That's going to equal mv squared over R. Now, in order for the bucket to not fall, that's going to be the special case where the tension goes to 0, or that's the critical case. So if we look at when this goes to 0, we can find that speed. So this is speed. Notice the mass appears in both of our remaining terms. If we cancel the mass and solve for v, you get that it's g root gr. If we put in our numbers for this case, for a 1.1 meter radius, and of course 9.8. When you take the square root of this, so this is basically 10, you get 3.3 meters per second. And so this is the velocity at the top. And I should say this is the minimum to keep the bucket from falling. Okay. How are you guys doing? Is that helpful to see another example? I know it's very similar to the situation that I mentioned, but this should be directly applicable to your homework as well. Yeah, the homework is due today. Most of the homework is friction, so it's stuff that we've already talked about. This homework assignment is a little shorter too. I think it's only 10 questions. Yeah, so don't forget to do the homework. Yeah, we'll do one more example. We'll do a car example. Yeah, that's the last thing that I want to make sure we get to. It's relevant to your homework as well, and that's a car. So let me show you. So this is actually the last section that we're going to look at. It's 5.4. And this gets at the connection between friction and centripetal acceleration. And it comes into play when we talk about banked curves. Okay. So the situation that we want to consider is another force that can provide the centripetal acceleration is friction. So and a good example of this is to think of, so we'll kind of talk about two different contrasting situations, banked and flat. And you intuitively, everybody I think has been exposed to this. You drive on the freeway, especially for high speed roadways. If you go around a corner, the road is banked. And that is, long story short, by tilting the roadway, by banking it, you're able to use part of the normal force to provide the centripetal acceleration. And it's kind of confusing to see where this is coming from. So we'll start with a situation where it's not banked, where it's just flat, and you can see what friction does, and then we'll look at the banked situation. So suppose you have, a roadway, and for simplicity's sake, it's just going to be, like a circular route that has some radius r. You have a car that's on the roadway. So this would be like the top view. And then if you were to look at it from like the back, you would see R, but the car is just sitting on the roadway. So there would be the car's weight is pointing down. There's a normal force that's holding it up. And then there's this centripetal acceleration. Oh, I've been drawing that in red. I'll draw it in red. The centripetal acceleration is pointed in. So we can see that in the top view as well. There would be a centripetal acceleration that's pointed in. And what's providing that centripetal acceleration is the force of friction. Okay. So of course the car would be traveling at some velocity, and we can't really see that velocity in the back view. Okay. Yeah. Yeah. So this is kind of weird. The thing, something that's sort of confusing about this is that it's really the static friction that's causing this. And you can think of that as that you don't want your tires to slide sideways on the road. So it's actually the friction from your tire on the roadway that resists its sliding that's providing the centripetal acceleration. So it, it's pointed in the same direction as uh, the centripetal acceleration in our picture here. But if we talk about it in terms of summing the forces, so sum of the radial forces, it'll be the force of friction is going to be equal to MAR, i.e. mv squared over r. What's the force of friction? Well, if we look at the top or the back view, we can see that the sum of the forces. And here, let me give you a coordinate system too. So the coordinate system that we're working with really is y and r. So if we sum the forces in y, like if you had just something that was sitting flat, you'd have the normal force minus the weight is going to equal the m times the acceleration in y, but it's not accelerating in y, so this would be 0. So in other words, the normal force is just the weight, like we've dealt with before. Yeah, so yeah, exactly. So it's part of what's confusing about this is that, you're also making use of friction to propel the car forward. But if you think about it, the tire is not sliding with respect to the car. So, or is not sliding with respect to the car, with respect to the road in the forward direction either. The tire is moving though, and so a different portion of it is in contact with the roadway. So you're using it to propel the car forward, but also using it to keep the car from sliding sideways. So it's doing two things. It's providing AR, also proportion, but are also propulsion, but uh, that's kind of a different issue. So the part that we're concerned about is the part that's providing the centripetal acceleration. So in other words, we know the force of friction gives our mass times centripetal acceleration. The force of friction is like we've been using before. It's mu times the normal force. We know the normal force is mg in this case. So it's going to be mu mg is mv squared over r. Notice mass is on both sides. So now we have a relationship between the coefficient of friction and the velocity and r. Which we'll use in an example problem in a second here. Now, this is all just a setup to give you the contrasting situation, which is if you have a banked curve. So now if we look at the back view, I'll draw it in the same way. It's difficult, sort of a perspective view. The drawing is going to not be very good, but imagine, it's sort of curved like that. The car now is at an angle. And we can draw in our forces. So we would have force of gravity that's pointed down. There's going to be a normal force that's at perpendicular to the surface, that's at an angle. And now, how we're going to think about this is the same coordinate system, r and y. And part of the normal force, so I should say, come on. It's going to be an angle theta. There's an angle theta here. It's the same angle theta there. So part of the normal force is just going to be, and I should really let me draw this bigger so it's a little more accurate. part of the normal force will just be what's opposing gravity. So that'll be the piece that's normal force cosine theta. And then part of it is going to be directed in the r direction. And that's going to be the normal force times sine theta. And then we also have still, of course, AR is pointed in the same direction, towards the center of the circle. And I don't want to spend too much of your time, but I do want to show you the rest of this situation. So in this case, let's do the same thing we've been doing. We'll sum the forces, look at the forces in R and Y. So if we look at the sum of the forces in Y, we have the normal force cosine theta, minus mg. And that's going to equal the mass times the acceleration in y, but that's 0 because it's not accelerating up and down. And then, but what this does give us is we can relate this expression to come up with something for the normal force. So if we solve this for the normal force, it's mg over cosine theta. So in other words, what's going to happen to this? The biggest that cosine theta can be is 1. So what this means is for angles that are smaller than theta, or sorry, that are smaller than 0, for angles that are larger than 0, the normal cosine theta is going to be less than 1. And so the normal force is going to be greater or equal to the weight. Okay. Now, if we look at some of the forces in the radial direction, we have Fn sine theta is the only force in R, and that's going to equal m times the acceleration in the radial direction. And now we have an expression for Fn, so we can substitute it in. Mg over cosine theta times sine theta. And we know what AR is. We can express that as v squared over r. So now we have an expression for that relates theta and v squared over r. And notice m is going to cancel. So it doesn't depend on the mass of the car. This sine theta over cosine theta, we can consolidate into tangent theta. And then we can divide this g over. So now we have an expression that, and what this means is we have an expression between the angle of the banking angle of the road, and the velocity and the radius of the circle. And what this means is, this is the angle should call this the banking angle that provides the centripetal acceleration without any friction required. Now, why we're looking at this situation instead of the case with friction is because this situation is simpler. If we add friction, it would help, but it would also be a little more complicated to analyze. So that's why we're starting, or why we're talking about this frictionless case. And that's what this is defined for. This is defined for without any friction. Questions? Yeah, so no friction. This is the no friction case. Where did mg come from? So The mg came from solving Fn cosine theta minus mg equals 0 for Fn. And then we just substituted in the normal force. So we substituted this in here. No, there isn't. There is not a homework problem that has friction in the banking problem. So it turns out it's kind of complicated to analyze if you add friction, because it depends. So remember when we've talked about friction before, the direction of the friction force depends on the direction that it would want to move. So it's always going to resist the motion. So in this kind of situation, if you're not going fast enough, you're going to try and slide down the bank angle. In that case, the friction would be pointing out. But if you're going fast enough, the friction keeps you from turning the corner, in which case the friction is pointing in. So it gets complicated quickly. So that's why we're not incorporating friction. So you don't have I don't think you have a homework problem that has friction in it, but you do have something that's about a roadway. But yeah, it doesn't involve friction. So I can show you one example with this if you like, but I don't want to stump on your time. But it'll be relevant to the homework. But I'm going forward, yeah, I need to be better about respecting everybody's time. So I don't want to run over too much, but I can show you one quick example. So let's see here. No, not this one. So here's an example of a problem that uses this idea. How large must the coefficient of static friction be between the tires and the road if a car is to round a level curve of radius 85 meters at a speed of 95 kilometers an hour? And what banking angle would give you the same acceleration? So let's look at this problem quick. I think this will help. So it's the same kind of situation, the flat situation that we've been talking about. If I can draw it here. So we have a car. And this radius is 85 meters. And the car is traveling at a velocity 95 kilometers an hour. And we're going to have a force of friction that's providing the centripetal acceleration. And the centripetal acceleration, come on, pen, is directed towards the center. And I was going to make it in red here. And so if we sum the forces in R, we're going to have the force of friction is the center directed force. It's what's providing the centripetal acceleration. It's going to equal mv squared over r. So we know that the force of friction, so if we look at this from the back like we did above, this is r, the car mg, normal force. We know that the force of friction is mu mg, And we can see that that's going to equal mv squared over r. Let's see. And then we can see, again, it doesn't depend on the mass. And we can solve this for mu. Now, notice our numbers are not in a nice unit. This is given in kilometers per hour, so we're going to have to convert that. We know that 1 kilometer equals 1,000 meters. We know that 1 hour, 3,600 seconds. That whole mess squared divided by our radius of 85 meters times g. And when we do evaluate that, we would find that mu s, remember this is static friction, equals 0.84 for this scenario. Okay, so questions. But we're kind of running out of time, unfortunately. But it's partly because we're having some good questions, so it's it's a good thing. But I don't want to take too much of your time. So this would be the coefficient of static friction that would provide the centripetal acceleration for the radius and velocity that were given in the question. And then, the second part of this, what angle would supply the same centripetal acceleration? Well, we can just use our tangent theta expression here. We already evaluated this quantity v squared over rg. It's the same size as mu s. So in other words, if we do the inverse tangent of v squared over rg, that'll give us the angle, and that corresponds to an angle of 40 degrees. So that would be the case where there's no friction. Okay. So that's the angle that would, without any friction at all, provide the same centripetal acceleration. Yeah, so, yeah, questions? Can you post extra videos explaining problems? Yes, I have one problem in mind that I can post. So you should have, most of the homework was about friction. There's some rotational centripetal acceleration stuff, and this, I mean, you should have everything that you need. There shouldn't be anything in there that surprises you. We've kind of talked about problems that are similar, kind of in the same vein. Yeah, I have kind of a fun problem that we didn't get a chance to talk about that I'll post a separate video for. So, questions? Yeah, shoot me a message if you run into something that's causing you problems, and we can talk about it. I sent out an email today. In terms of like office hours and stuff, let me know if you want to meet, and then we'll meet. I've been watching that, and there hasn't been a lot of people using it, so I'm not going to watch it as actively, but you can just contact me and we'll meet. Other questions? Um, so I'm happy to stick around for those that have questions, but for others that need to bounce, that's totally fine. Have an excellent weekend. Stare at some things that are further than 20 feet away. Maybe read some paper books or something. Um, and then we'll meet up next week and we'll start talking about gravity. Okay, I'll just type in here.